resistivity, etc., one can understand the kinetics behind any electron transfer reaction, catalytic reactions, and also in the field of sensors, energy storage devices, etc. It's very useful technique. Okay, so maybe due to lack of time, I will not go into very fundamental of this impedance spectroscopy. But if anyone is interested, I can always share these things through email or through questions later. Okay. Among the many different electrical circuit element like resistor, capacitor, etc., the resistor is frequency independent. What do I mean by that? Whatever be the frequency you change, the resistance is not get affected. Okay. So only the capacitance and the Faraday component of the impedance like RCT, Warburg impedance alone is affected by frequency. That's why the very first point of your measurement at the highest frequency, at a high frequency, okay, highest frequency of study would give you the value of Ru, R omega. When you go from high frequency to low frequency, there is a change from a charge transfer controlled process to diffusion controlled mass transfer process. And the frequency at which it switches over from a charge transfer to mass transfer is called knee frequency, knee frequency, and the corresponding time constant is called tau naught. That is very critical in case of energy storage devices, because this frequency would provide information about how fast you can deliver the stored charge at your material. Do you get me? The frequency tau naught would provide information about how fast you can deliver the stored charge at your interface. So this is the kind of impedance measurement one would get for a mixed control regime. Okay, so this is for a purely diffusion controlled process. And this is for a purely charge transfer controlled process. But in case of just the capacitance alone, what behavior you would get is, you would get a typically straight line which is parallel to Z imaginary axis. The corresponding phase angle change for capacitant would be 90 degree. Okay, maybe I'll show you the example at later part. Now, why do we use two different kind of representation as an output in impedance? It's called Nyquist and Bode. Okay. In case of Nyquist plot, as you have seen a while ago, you cannot pinpoint the frequency dependence of the impedance. Okay. So what do I mean by that? You cannot measure the frequency directly from this kind of output. Rather, by looking at the Bode plot, this is a kind of phase angle change. I mentioned for a typical capacitive behavior, you would get a 90 degree over the frequency range. So by looking at this kind of plot, one can assess this is the frequency, this is the time duration, your material will exhibit a pure capacitive behavior. Do you get me? This is the time duration, this is the kind of frequency range. Your material would exhibit pure capacitive behavior because it exhibits 90 degree throughout this frequency region. On the other hand, in case of Bode frequency plot, the total impedance is measured against a log frequency. Okay, so you can able to explicitly understand the frequency dependent from Bode plot, which is not the case in Nyquist plot. That's the kind of major difference between Nyquist and Bode. Now, we do fit the impedance measurement to different circuit element. Why do we fit that to a circuit element? Because you can directly correlate the structure of the interface and you can directly measure the quantified parameter. What do I mean by that? Let's say you can directly correlate the electrode-electrolyte interface to different circuit element. For example, the moment you dip any electrode into an electrolyte, I mentioned yesterday that it forms a spontaneous double layer at interface. So it exhibits a capacity behavior, capacitance at interface. And in order to establish this double layer structure, the electrode will exhibit a resistance that is called resistance from the electrode, okay, RP, polarization resistance, etc. Apart from this, we do have resistance arises from the electrolyte component, and that's how you correlate a typical electrical circuit element to electrode electrolyte interface. How do we understand this process? I used to tell a joke during my lecture in the class. For example, let's say your mother is cooking, okay? Just give me a minute, I'll take some water. Let's say your mother is cooking in the kitchen, okay? And you guys are sitting and watching TV aramsa in the sofa. So your mother suddenly received a phone call. She said, Papa, why don't you go and start frying? Do you guys get up from the sofa and go and start frying your sabji immediately? You don't do that, right? Now, rather, your mother keep on shouting at you, then come to a singular and start scolding. Then you would get up and go and start frying, right? So, meaning you would exhibit resistance to function immediately, but with the constant persistence, you can get up and start going and frying. Similarly, electrode electrolyte interface would also behave a similar way. By applying potential, more and more potential, you can able to polarize the interface, and that resistance is explicitly mentioned as RP or RCT in case of electrode electrolyte interface. So that's why I'll go back a few slides. That's why you would use many different circuit element like resistor, capacitor, Warburg impedance, a constant phase element, inductor, etc. Now, in the case of semicircle, if you observe a perfect semicircle, then you can fit capacitance, okay? Then you can fit capacitance as your interfacial parameter. But if you don't get a perfect semicircle, suppose if you get a depressed semicircle, then you can fit what is called a constant phase element, okay? Q, constant phase element rather than capacitance. Now, this is a kind of typical output one would get in terms of Bode, and for a complete charge transfer resistant, this is the kind of output you would get in Nyquist. Now, okay, suppose I am, without discussing a catalysis, I am directly showing as an example for a output in impedance. Let's say you have prepared a catalyst to carry out a fuel cell reaction. Let's say a cathodic process of oxygen reduction reaction. Okay, so when you keep on cycling your catalytic material, you would see that the RCT increases from initial cycle to 300, 600, about the 900 cycle. You see that the semicircle keep on increasing, meaning RCT increasing. So that suggests that your catalytic material exhibit a higher charge transfer with respect to cycle. So it essentially loses the stability over the period of cycling. So that kind of assessment one can make, and this is the kind of capacitor what I mentioned earlier. If you develop a electrochemical double layer capacitor or super capacitor, the typical output in impedance would look like a straight line, which is a kind of parallel to imaginary axis. Okay, so this is the kind of behavior you would get for impedance. And the output in terms of Bode phase angle plot would be a typical 90 degree. Slides, and directly I will talk about catalysis. Is it okay? I remember I spent too much time, but I think that is useful for you guys. Now, maybe I will, just to highlight importance of these techniques. Then I will get to catalysis maybe in the last 15 minutes or so. Okay. Now, the techniques like rotating disc electrode, rotating disc ring disc electrode became very popular in recent time because of the importance to fuel cell reaction, mainly oxygen reduction reaction. Okay. Recall the very first lecture I mentioned that diffusion is the predominant mass transfer, and that is the rate limiting step in most of the cases. How do you overcome diffusion? You can overcome the limitation of mass transfer by rotating the solution, okay, by stirring the solution, so that you can have enhanced mass transfer. And that's where these techniques become most popular. Why do we use such techniques? You can overcome the limitation due to diffusion, so that you can measure kinetics of any electron transfer reaction very precisely. Okay, so I will skip the slide and directly talk about Lewis plot. This Lewis equation provides a relationship between limiting current and directly with respect to rotation speed. Okay, when you rotate the speed, how the current changes, that relation is provided by this Lewis plot. A slight modification in the equation is provided by this Lewis plot. This is the most famous equation in case of RDE, RRDE experiment. Here, inverse of limiting current is correlated with the rotation speed. Okay. These are the typical components one would get in case of RDE. The advantage of moving from rotating disc electrode to rotating ring disc electrode is the following. Let's say, suppose you monitor oxygen reduction reaction. Okay. What are the products in oxygen reduction reaction? If it undergoes a 2 electron reduction, it provides hydrogen peroxide as a product. And if it undergoes 4 electron reduction process, water is the product. Okay. And if it undergoes partially reduced oxygen species, rather than 2 and 4, if it undergoes 2.3, 3.2, 3.5, etc., the oxygen reduction reaction would result in a partially reduced oxygen species. And those kind of product analysis one can do at the ring electrode. Do you get me? One can do at the ring electrode. This is a kind of glassy carbon working, disc electrode and platinum ring electrode. So whatever the reaction you carry out at disc, the product you can able to get at the ring electrode. Do you get me? So you can use a bipotentiostat. You can use a bipotentiostat to control the potential of both ring and disc, so that you can carry out the reaction at the disc and analyze the product at the ring. It's a very, very useful technique. Not necessarily the oxygen reduction. One can also analyze any kind of electrochemical reaction, like enzymatic reaction. For example, the glucometer which is available in the market, the enzyme glucose oxidase converts glucose to gluconic acid and hydrogen peroxide. The liberated hydrogen peroxide could be detected at the ring, so that you can bias the potential of the ring in such a way that either you can monitor the reduction or oxidation of hydrogen peroxide. The critical parameter in such kind of RDE, RRDE experiment would be collection efficiency. That's what I showed in the previous slide. Collection efficiency, the capital N value. One can determine, normally they would provide with the electrode itself. It can vary between 0.2 to 0.25 value, but one can determine experimentally also by using ferroferry redox system, and by measuring the ratio of ring current with respect to disc current, one can determine the collection efficiency. That becomes a very, very critical parameter in RD and RRD experiment. Now, electrochemistry is not just about cyclic voltammetry, impedance, pulse voltammetry technique. The techniques moved on. Now we have technique like scanning electrochemical microscope, where one can image the sample substrate. especially with respect to catalysis. Whatever the property you observed is the average property of the system, the average property of your material. And the material may have catalytically active sites distributed over the surface of the catalytic material. One can image such kind of catalytically active site. Rather, we used to define that as birth of electrocatalysis. One can understand using this scanning electrochemical microscopy technique, thanks to the living legend of modern electrochemistry. He is Alan J. Bard, who is the man behind discovery of the scanning electrochemical microscope. I would again say that he is the living legend of modern electrochemistry. Okay, so he has developed this technique where one can image not necessarily the catalysis material. One can analyze sensor, one can analyze the enzyme distribution, etc. using this scanning electrochemical microscopy technique. Maybe I will just skip a few slides. But remember that one can image, at the same time one can carry out reaction. That's the kind of nanoparticle distribution over the surface. Wherever you observe a high current, you are measuring the current due to electrochemical reaction. Okay. Now, how long I can talk now? Hello, can you tell me how long I can talk?
Sir, the next session is scheduled at 2:30, maybe until 1:15, sir, so that we can have lunch break.
Up to
1:45 or 1:50-ish.
Okay. Is it okay with the audience too? I'm okay. I can talk, not a problem. Okay. Let's see how far we go with this.
Yes, sir.
Maybe up to 140, 145. Let's see how long we go there. Okay. Right now, so that's about the fundamental concepts in electrochemistry and the technique. Of course, I do work on both sensing and electrocatalytic area. Our group focuses on many different catalysis, not necessarily water splitting alone. But today I will only talk about water splitting. Okay. Now, if you look at the catalysis research, this is broadly been classified into 5 different categories. One is a biocatalyst. The second category is a homogeneous. Third, electrocatalysis. And fourth, conventional heterogeneous catalysis. And the fifth one is modern area of ultra high vacuum surface science based catalysis. Okay. So our group essentially focus on both bio as well as electrocatalysis. Maybe I will spend a minute or two in biocatalysis. What do I mean by biocatalysis? You can look at enzymatic reactions. You can create biomimic catalysis. You can mimic the function of biomolecules both in terms of structure and in terms of its function. Okay, both one can mimic even on the electrode surface. So that's the kind of biocatalysis we talk about. What do I mean by electrocatalysis? The very famous reaction would be water electrolysis. So why do we worry about water electrolysis? We can have a very big debate on this water splitting reaction. There are people even now, they suffer for water for even drinking purpose. But why do you want to split water into hydrogen and oxygen? No idea. We can have debate later. But right now, in case of electrocatalysis, we do have water electrolysis and fuel cell reactions. What do I mean by fuel cell? Mainly the oxidation, oxygen reduction reaction at cathode and oxidation of fuels like methanol, ethanol, CO2 conversion, etc. in the anode chamber. So those reactions comprises of electrocatalytic reaction. And when you develop material to tune this reaction and to enhance this catalytic processes, those materials are called electrocatalysis. Okay, so in a way, electrocatalysis is defined as a process in which the electrocatalyst is being used. What do I mean by electrocatalyst? It is the ability of the substance or a material that could be used either as an electrode surface, or you can modify the electrode surface with that material that could be used to accelerate the given electrochemical reaction or given electrochemical process. For example, we can use platinum as an electrode to carry out methanol oxidation reaction. So here methanol is a fuel. When it undergoes oxidation, remember in a fuel cell reaction, oxidation occurs at anode, reduction occurs at cathode. So the methanol oxidation occurs at anode reaction. So we can use material like platinum, carbon, or any kind of modified material that can accelerate methanol oxidation process. Okay. So this is where I was talking about. We can have even enzymes that can mimic such kind of oxidation process as well. Now, in case of water electrolysis, there are three famous reactions as far as electrochemistry is concerned. In fact, it is an advantage as well as a disadvantage for electrochemical studies. Suppose if you use water as an electrolyte, your potential window of study is limited, because the moment you scan the potential in the positive direction, water splits, water undergoes oxidation to give you oxygen. So the oxygen evolution reaction is a limiting step when you use water as an solvent or water as an electrolyte. And when you scan the potential in the reverse direction, initially there would be oxygen reduction reaction, okay? And when you keep on scanning the potential further in the negative direction, you would end up in a regime where hydrogen evolution reaction occur. So hydrogen evolution reaction, oxygen evolution reaction, and oxygen reduction reaction are the limiting factors, and that will decide the potential window of your study. But in case of electrocatalytic process, this becomes very, very useful. So why do we worry about this water splitting reaction? Yesterday I mentioned that thermodynamically, maybe I do have the slide, I think, yeah. Thermodynamically, water splitting reaction is not an allowed process. Probably whomever studied thermodynamics would know. It is not an allowed process. Delta G is positive. It is roughly about 237 kilocalories per mole. I can show the calculation a bit later. Delta G for water splitting reaction is 237 kilocalories per mole. But when you apply a potential, delta G is minus NFE. So when you apply a potential, you can tune delta G from a positive to negative, meaning non-spontaneous to spontaneous reaction, so that you can split water into hydrogen and oxygen. Hydrogen and oxygen both could be used as a fuel. That's the advantage of water splitting reaction. Okay, that's why nowadays people talk of using water as a fuel to drive vehicle, right? By applying 1.23 volt, you can split water into hydrogen and oxygen. Hydrogen will evolve at cathode and oxygen would evolve at anode chamber. Now these are this is what I was talking about, the EMF series yesterday. You can decide upon, depends upon the potential value, you can decide which one could be used as an anode and which one could be used as a cathode. For that, the thermodynamic potential value of water splitting becomes very, very useful. Okay, so this is what I was talking about, right? When you go in the positive regime, at 1.23 volt, water split, oxygen evolves, which undergoes typically a 4-electron process, evolves. And the moment you reverse the scan direction, initially oxygen reduction happens, where the oxygen gains that 4-electron, undergoes reduction to give you water as a product. And when you keep on going in the negative direction further, water splits into hydrogen. So hydrogen evolution occur. Okay, hydrogen evolution occur. When you do a cyclic voltammetry, you would observe that when you go beyond about -1 volt or so, you see a very large current. And sometimes at the counter electrode, you would see bubble formation. You know, I'm sure whomever, doing PhD in the field of electrochemistry, you would not reveal these things to your guide. I know. Suppose without knowing you apply a very high positive or negative potential, suddenly there would be a bubble formation in the counter electrode, and you would see that something you did mistake. It is not a mistake. It is that we do not understand the process. Okay, the bubble would occur at a counter electrode. That is because you apply a very large over potential that solvent itself undergoes a splitting reaction to give you hydrogen. That's the kind of observation you would make. Okay. Now, what is the advantage of using catalyst? Let's say in case of oxygen reduction reaction, if you do not use any catalyst, the oxygen reduction would occur at a large over potential. But the moment you introduce any kind of catalyst, you can gain the over potential, meaning reduction would occur at a very positive potential. You gain an over potential, and it can also provide a stable steady state current. So you can shift the over potential as well as you can maximize the reduction reaction. These are the two parameters one can look for in the development of catalyst. Now, you can critically evaluate the catalyst using these three different parameters. The first one is activity, the next one is stability, and the third one is selectivity. All these things become a very, very critical. This is where you play around with the material in terms of adjusting the potential. Okay, suppose if the water splitting occurs at the over potential of 600 millivolt, you want to play with the activity so that you can reduce the over potential. That's the first point. And the second point, not just the activity alone. Your catalyst should be stable enough, meaning the prolonged water splitting should give you oxygen evolution or hydrogen evolution for a longer duration of time. That's about stability, and it should be selective. Okay. Suppose if you have a water and alcohol mixture, your catalyst should be selective to water splitting reaction alone. It need not split alcohol into a lower carbon fraction products. Okay, so these are the three parameters. Of course, one can play with these things to maximize the electrocatalytic reaction. And electrochemically, you can evaluate and understand